long week this week. We last week was spring break, but during that week Stephen Hawking passed away, as many of you know, and we held a special remembrance in his memory at the Black Hole Initiative. There was a very moving half an hour presentation by Malcolm Perry, followed by some comments by Andy Strominger, and the video of that was just placed on YouTube, and Nina Zonneville will send it around the link to that, so everyone is encouraged to watch it. And the funeral will be in a week and a half, and I was invited to go there, and we represent all of us there. It will be a family event, a relatively small number of people will be there, so it should be interesting to see who is there also. But otherwise, things are going great over here, and we just had an excellent talk by Xin Lu, that's visiting us from Illinois. Right here. And she used to be a postdoc in the upper floor, just above the theory, above the ITC, because she's an observer, so she's closer to the sky. And Xin is also married to Yu Shen, that many of you remember was a postdoc at the ITC.
Yeah, also here.
Also here, and also working on a binary black hole system, so it's a family business. But we'll start with Mislav Balokovic, who is here as a postdoc at the Black Hole Initiative, and he will talk about what obscures AGN, insights from broadband X-ray spectroscopy. We were supposed to hear from Gerry Gilmore from the University of Cambridge, the other Cambridge. The real Cambridge. The other Cambridge. The other. We'll have some ancestry in England. And his flight didn't make it because of the weather. And so we hope that there will not be any more nor'easters. This is it always happens when we have prospective students visiting us. That's how I can put it. So instead, we will hear a very interesting presentation by John Forbes, our own, and he will talk about the evaporation of planetary atmospheres by quasars. So quasars are the theme today, looks like. Then we'll hear from Xin again. She will talk about a candidate Tidal disruption event in a quasar at a redshift of 2.359 from abundance ratio variability. And finally, we'll conclude on a topic unrelated to quasars, and we'll hear from Federico Fraschetti, who is spending time at the CFA and also at the University of Arizona. And he will talk about the Crab Nebula, particle acceleration and escape at shock waves. Mislav.
Hello, everyone. Oh, it's working. My name is Mislav Balokovic. I'm one of the Black Hole Initiative Fellows down at the Black Hole Initiative, 20 Garden Street. Being fairly new, I appreciate the opportunity to be here to talk to a broader CFA audience about my interest, which includes AGN. I won't talk about what AGN are. I'm sure many of you know, but this is going to be a talk on X-ray spectra. So I'll remind you just where the X-ray spectra of AGN come from. In this sketch over here, we're seeing a supermassive black hole, some material around it accreting, and this explosion of orange here is what we call the corona, is the rarefied hot plasma that emits the X-rays. And the spectrum of that corona is typically a power law, or if you want to go into detail, a power law with a high energy cutoff. But for the most part, AGN spectra are power laws. Unless you obscure them, and this blue part from the last slide is now all in here. There's material at larger scales that obscures our view directly of the corona. And so these different colorful observers correspond in their color to spectra shown on the right, where the one shown in black here is looking straight down and seeing this power law spectrum from the innermost part. And progressively, as we go down towards the blue observer, more and more of the spectrum is absorbed, and that results in this photoelectric cutoff at the low energy end. Until in blue, we see the spectrum that actually contains no component along the line of sight. Everything has been extinguished, and all we see is light scattered in the structures around the AGN. Here's another spectrum. This is the cosmic X-ray background, the diffuse light that we see combined from all AGN that ever existed, measured by many, many telescopes, shown in colored points. And we understand that spectrum as, through its components. If we just assume all AGN are obscured, then the joint spectrum would look like this, which clearly does not match the shape of the cosmic X-ray background. We have to add two other components. You can assume that it's one component. It's obscured AGN. It's just the heavily obscured ones here in black, and in blue, lightly obscured AGN. So when we add that in, we can match the spectrum of the cosmic X-ray background. And that implies that there's a huge quantity of obscured AGN somewhere at high redshift where we can't really observe them directly because, as I said, obscuration causes the soft X-ray flux to be absorbed. Here's another way to show that at high redshift there's lots of obscured AGN. They constitute about 50% of the population locally. But if you look at higher redshift, this is one way to show fraction of heavily obscured AGN is tending to go up, increasing the fraction in the population. This is another way to show it. Space density of AGN generally goes up with redshift, up to redshift 2 for all sorts of AGN, but it does so more for obscured AGN, which are shown here in blue and green, compared to unobscured AGN, which increase less. So that means that the fraction is higher at higher redshift. So they're important to just account for all the supermassive black hole accretion in the universe, if for nothing else. I haven't really mentioned what is it that obscures AGN, because it could be a number of things, and that's exactly what I'm interested in. It could be, like in this case over here, for Centaurus A, you can see that the dark lane is stretching across the center of the galaxy where the AGN lies, and producing some obscuration. But in most cases, in local universe, we think that there has to be another relatively compact subparsec component that we like to call the torus, because it could have a roughly toroidal shape that is responsible for the heaviest obscuration. And that may be related to winds and outflows that usually take a conical shape, and those two structures may be related. And as we know, winds and outflows may be relevant for evolution of AGN host galaxies, or just generally galaxies that host black holes, which is most of them. So how do we learn about these structures? As I said, there's gas around the supermassive black hole, and this X-ray light that hits the gas around supermassive black holes produces additional components, and here I'm components in the X-ray spectrum. Here I'm highlighting only two that are the most important. You see an iron line. This is fluorescence line at 6.4 keV, and also Compton hump, a broader structure feature that peaks roughly at 30 keV. So those are signatures of matter, whatever its distribution is, around the black hole. We have some models for this. We're quite limited to what kind of geometries one can try to deduce from the data because of the limitations of data quality. And I've listed a number of calculations here. Only a fraction of them resulted in models that you can actually fit to the data. And those that are highlighted, I've actually put their geometries on the left here. So there are something like a donut of uniform density, or something like a spherical distribution with cutouts in the polar regions filled with individual clouds. And my favorite is the one in the middle here. This is my model published earlier this year, which is essentially a cloud distribution averaged to an average column density with some cutouts in the polar regions specified by this opening angle here and some average column density, which these two parameters seem to be the main parameters that matter for the data we have. Oops, sorry. How does this work? This is, again, a little bit of a simplification. On the left, I'm showing 4 different tori with 4 different opening angles, going from about 90% covering to about 10% covering. If you're sitting at the black hole looking out, that's the percentage of the sky that will be covered by this structure. And I'm showing 2 spectra for the extreme cases. In the case of 90% covering, these dashed lines show you what is the contribution of scattering from that kind of a torus. And in the other case, the blue spectrum is for 10% covering. It clearly gives a different spectral signature. You can look specifically at the iron lines around 6.4 keV and the Compton humps, and they clearly have different shapes and different strengths relative to the intrinsic continuum, which is shown in dotted lines. So if you have good enough spectra that you can distinguish these situations, then you have a handle on the geometry of the material around supermassive black hole. And I'll point out that this energy band between 3 and 70 approximately keV is traditionally not covered with soft X-ray telescopes. So the data you actually need to be able to do this is from NuSTAR, which is a relatively new addition to our X-ray telescope arsenal. So this is from my work published about a month and a half ago using NuSTAR data, where I applied this model that I mentioned 2 slides ago onto NuSTAR data of high quality. You can see the individual spectra here. These different colors are for different AGN in the local universe. And you can see this is the data. So the error bars are so small that they're covered with a line. And they're good enough that we can distinguish these additional components. This is the signature of the torus. This is the signature of a different torus. This is the signature of a different torus. This one as well. These tori have different parameters. And I summarized them on the left here in the parameter space of covering factor versus column density of the torus. And you can see that looking at either 1, 2, or 3 sigma contours, they occupy different regions in this diagram. For example, this one is at relatively low density. It covers most of the sky, so you can wonder, perhaps this is just a galaxy. Maybe there's no compact, dense part that we usually call the torus. This one, shown in green, has only a small covering factor, so that's more like a ring. If you look at the sky and the Milky Way, that covers about 10% of your sky looking from the Earth. So maybe that's just the outer part of the accretion disk, and again, maybe there's no traditional torus in this object. And for example, these 2 are highly covering dense tori, perhaps what the classical picture would tell you. So the point here is, so these 4 demonstrate just the different tori that we can find in the local universe, but they are 4 different random AGN. They don't tell you much about the population, but I've done very similar work, actually the same work, on about 130 for my thesis, and that's because this is a short talk, I can't go into that in much detail, but I'm very happy to talk to people if they're interested about that. Of course, this is one of the techniques that we have. It's relatively new. It's been underused so far because of the lack of data, but there are others that we can combine with this new method to learn more about what obscures AGN. And for example, people here in particular have worked on monitoring of nearby AGN, where you can see individual clouds from the torus or the broadline region passing through the line of sight. So that constrains statistics of these clouds, their density, the number density, and the distance, because they will travel faster if they're closer to the black hole. Furthermore, we can also use Chandra to resolve some of the emission in the local AGN. So for example, over here I'm showing a sketch. This inner part cannot be resolved even with Chandra in the nearest AGN. But the outer parts that perhaps belong to the galaxy or could be associated with the ionization cone, along which we have, in at least some AGN, we know outflows happen, we can resolve those. But there's no self-consistent model that would allow us to understand these observations completely. So this is something we can improve in the future. There's also other methods that we could use in the future. You could also look at multi-wavelength data, infrared in particular, because these clouds absorb X-rays, but then we radiate that in the infrared. And also look at the optical narrow line region, broad line region. Geometry of all of those is related to one another because it's an integrated system, although we like to think about these components as being separate. So just summarize quickly, I hope I've convinced you that there's a multitude of obscured AGN at high redshift, and they're important to study if we want to understand accretion in general. Whatever is obscuring these AGN leaves signatures in the X-ray spectrum, and with high-quality data now and good models, we can get a handle on constraining the geometry of the obscurer. In the future, we hope to combine that with other probes of structure and hopefully understand what is it that obscures most of the supermassive black hole accretion. Thank you. Right.
And that's roughly where the Thomson optical depth is unity.
Yes.
Is there a physical reason you think behind it, or do you think it's
I don't know yet. It might be that it's not a coincidence. We don't yet have models that tell us much about it. But yes, it's true in general. If you look at the larger sample, that on average these tori tend to cluster around the optical depth, which corresponds to unity for Thomson or Compton scattering.
possible that they start from smaller radii and when they're opaque, they somehow get pushed out until they reach, or get inflated until they reach this state?
Yeah, I think that's a possibility, definitely.
Comments or questions?
So have you seen any correlations between your torus parameters and other properties of the AGN of the galaxy, black hole mass?
Yeah, I can. Well, these are obscured AGN. It's typically very difficult to get their black hole masses. I would be very interested in trying something like that in the near future. I can tell you that in some cases, these parameters that we derive from X-ray spectra correspond to parameters that can be derived from infrared spectra, for example. And that's very cool. That's telling us something about relative distribution of gas and dust, because dust is primarily, infrared is primarily due to dust, and X-ray obscuration is primarily due to gas. So it's not clear whether they should be matching, but so far they do.
Yeah, I have a question.
Please.
Going back to your constraint on the column density is a kind of technical question. So when I see these different shapes in the confidence intervals, like the 390 is elongated this way, but it's almost perpendicular.
Oh, these are degeneracies. Yeah. So
Why is it like different directions or different? Is it just the observing angle of the source?
it could be complicated, but I have not investigated this in great detail. It also depends on just the quality of the data. You can notice, I mean, all of these are high quality data, but they're not quite the same. It also has to do with strength of the line versus the shape of the Compton hump. In this example in particular, there's not much of a Compton hump. It's kind of flat. In this case, it's really pronounced. So it's different. I just don't think it's trivial. But there are definitely degeneracies, and they depend on both the data and the model.
Any other comments or questions? If not, let's thank Mislav again.
Thank you.
All right. Hello, everyone. So after that very nice introduction to black holes, I want to talk about something that touches on black holes, but along with two other things that sort of don't often touch black holes, particularly planets and the distribution of planets in galaxies. So the idea here, I'm maybe giving away the punchline here, is that quasars can do some real damage to the atmospheres of planets. So let me go through that argument. Okay. So let's start off with this nice picture of the Earth. You can see, as we all know, Earth has an atmosphere, and it's very thin. And there are many things that can and do happen to planetary atmospheres. So this is sort of a cartoon summarizing all of them I could think of, but I'm sure there's more. So you have radiation from the star, which can, if the planet is close enough to that star and receiving enough radiation, drive what's called a hydrodynamic wind, where the particles sort of behave collisionally. There's on the other side of that, where the radiation isn't that strong, you can also get Jeans escape, where individual particles that are sort of at the very tail end of the Boltzmann distribution exceed the escape velocity. You can also have particles from the solar wind come in, create local ionizations. You can also have things hitting the atmosphere, and even things from far away, supernovae, GRBs. Usually what these tend to do is change the chemistry of the atmosphere, not really the mass. So the question is, what happens if we think about black holes? What can black holes do to planets? So to make a simple estimate here, we can use an extremely simple argument, and the formula you get at the end can be derived in, from two considerations, but it's very widely used. I'm not just making this up. So basically, if you take a planet and you look at the energy it receives in the XUV band, so photons high enough energy to ionize hydrogen, or nearly so, and you just look at how much energy it receives, you can compare that to the energy per unit mass that you need to unbind a little bit of mass from the atmosphere of the planet. And if you equate these, you get that the mass loss rate is just this formula proportional to the flux, inversely proportional to the mean density of the planet mass over planet radius cubed, and some efficiency factor epsilon in front. So now this is where things get really surprising. If you plug in some numbers, so if you make some assumptions for how bright black holes are, and you plug in some fiducial numbers, so like a 10 to the 9 solar mass black hole, Eddington ratio approaching unity, and a radius of a kiloparsec, so it's sort of galactic scales, you get that the mass you lose from a planet is not insubstantial. So the sort of fiducial value here is 10 to the 22 grams, and if you compare that to sort of a few handy measuring sticks we have from our own solar system, you can see that this actually exceeds the whole mass of Earth's atmosphere. So now, given this sort of surprising result that planets out to kiloparsecs can lose a good chunk of their atmospheres, the question I wanted to ask is, what happens if you take a random planet in the universe? How much mass does it lose? So this is a pretty simple calculation. Basically what you do is you take a random halo in the universe. You know how common halos of that mass are. And then using an approach similar to what James and Avi did a few years ago in a different context, you can, once you know the halo mass, you can estimate the stellar mass observationally. You can, from that, estimate whether the galaxy is quenched or star forming and how massive its bulge is. And from that, you can sort of empirically, at every step of the way, estimate the black hole mass, the disk mass, the size of the disk, and the bulge of the disk. So this determines where the stars are relative to the black hole, how massive the black hole is, and that determines how much mass you lose. So putting that all together, this is what happens to a random planet in the universe. So there's a lot going on here, so let's step through this a little slowly. So the x-axis here is how much mass you actually lose, and I've highlighted our convenient units here. The y-axis is the cosmological density of stars, which we're assuming is related to the cosmological density of planets. So this is sort of the number of planets per co-moving cubic megaparsec. And what you can see is, and so the lines are at different redshifts stepping forward. So we start at redshift 10, and then we step forward to redshift 0. And the different lines here, so solid is all the stars, and the dotted line is just highlighting the bulges of galaxies. And so there's a lot going on here. So the first thing that's going on is that the mass of stars in the universe is growing. So these lines are increasing in normalization. They're also, starting at redshift 10, they're moving to the right. And what's happening there is that the black holes in the universe are growing along with the bulges. So as the black hole gets more massive, it shines more, and more of the stars are affected. But you can see that it actually doesn't go that way forever. It starts going left at low redshift. So less of the population is subject to this effect. And what's going on there is that at low redshift, the black holes have stopped growing, but the galaxies are still growing. So the stars are getting further away from the black holes. And what you can see is that these units of measurement that we have go sort of down the middle of the distribution. So just like with our order of magnitude effect, you can see that sort of a substantial fraction of planets in the universe are subject to these things. So we can split this up by mass. So if you look, so the punchline here is that most planets in the universe have lost about a Mars mass worth of atmosphere due to quasar activity. And this is occurring mostly in sort of the highest mass galaxies that have the biggest black holes. So now what we did, so that's sort of a cosmological picture. What about our own galaxy? So after we posted that paper, I got an email from Howard, who's a grad student at Northwestern, and he's a real planetary scientist. So he has a model for the evolution of planets subject to mass loss. Obviously, usually people are thinking about the mass loss due to the host star, but you can just as well apply that formulation to the supermassive black hole. And so he set up a bunch of MESA models that explicitly evolve the structure of the planet and how much it loses mass. And then at some point in the evolution of that model, he turns on the AGN and sees how much, what happens to the planet. And the effect can be pretty dramatic. So if we think about this in units of galactic-centric distance, so what he did is set up a grid of models at different distances, different ratios of planet, different masses, and these planets also have different core masses within them. And if you start all the planets off as gaseous, and then at some point between the initial conditions and 10 gig years later turn on the AGN, basically you can, for the closest planets, you basically completely transform them into Earth-like planets. So you're taking sub-Neptunes and transforming them into super-Earths. And the result of this is that you end up with a very high density of terrestrial planets in the centers of galaxies, especially ultra-compact dwarf galaxies. So this is a plot of the stellar mass of whatever system I'm showing and our estimated density of the number of terrestrial planets in that system. And the red here is what happens when you add in this effect, if you assume that these have a black hole of the appropriate size. So basically, for nuclear star clusters around the centers of supermassive black holes, they're sort of, they can get quite dense at the low mass end, and this is a large effect. But the place where this effect is really dramatic is in ultra-compact dwarfs, which have large masses but very small sizes. So you can have extremely high densities of planets, terrestrial planets there. So just like it's the flu season, just like if you sneeze in a crowded train car, this may have implications for how common life is in the universe and where we might find it. So that's it. Thanks.
Does ISM not shield the planets from?
Yes, it's interesting that Mislav just gave this talk on obscuration, and I didn't mention it. Implicitly what we're assuming here is that this is all happening in the quasar phase. So when the black hole is brightest. So we argue that the ISM has sort of a secondary effect in that it's usually blown out, and these are elliptical galaxies where this is usually happening. But it is probably an important effect that we haven't considered.
So the mechanism by which you transform a gas planet into a terrestrial planet, yes. I assume there's a core inside the
yes.
gas planet first. And so you get rid of the envelope.
Yes.
So you don't expect to still have an atmosphere of that.
Yeah, that's right. But I mean, there are other things that could regrow the atmosphere in the end. And we don't have an explicit model of that, but that's what we're speculating.
What were you assuming for the quasar duty cycle?
So what we assumed, so way back at the beginning, I showed basically the formula we ended up using, and we're simplifying all of that down to a time scale of 40 million years during which the quasar is active. So that's an order of magnitude estimate, but it's sort of linearly dependent on that.
Yeah, just a follow-up question to that. So did I get this right, that the effect really depends on the total sort of integrated luminosity during the quasar phase, so less dependent on the actual cycle, if it's really episodic or is
Yeah, it just depends. It just depends on the total fluence of the planet.
And
Yeah.
also, this is really interesting, but I guess I didn't realize that our central black hole could have such a large effect on us. I always thought that the sun.
Not on us.
Yeah, it is. I mean, like perhaps not a coincidence that we live in the outer part, but not in the center. But I was wondering how this depends on the chemical composition of the atmosphere.
Yeah. So.
In terms of like hydrostatic escape, for example, do you need like a hydrogen-dominated?
Yeah. So if you use this formula is only really well understood and well utilized in hydrogen-dominated cases. So you can think of, if you change the composition, you can think of that as changing epsilon. And that changes epsilon. It can reduce it by up to a factor of 10, but that's still an area of active research. So strictly speaking, this is only applicable for hydrogen atmospheres.
That's the question, Gerry.
Well, you may have just answered the question I was going to pose, but I would imagine that this process could have a rather dramatic effect on the chemical composition of an atmosphere insofar as far UV and X-UV photons will photo-destroy molecules.
Yep.
And any hydrogen, free hydrogen that is liberated in the process will preferentially escape relative to oxygen, nitrogen, carbon.
Yeah.
So I'm wondering whether you've given some thought as to what would remain after this process, which preferentially depletes the atmosphere in hydrogen.
Yeah, I mean, given all the uncertainties, we haven't. But yeah, I mean, that's obviously a very important aspect.
But we should all be grateful that we are in the suburbs of the nuclear.
Yes.
Thank you very much.
Well, okay. Can you hear me? Yes, okay. All right, so go back to the evil side. This is the work that, so this is just a pet project, so extending the family business, I guess, but a candidate tidal disruption event in a quasar at a ratio about 2 from abundance ratio variability. So complementary to the traditional method of identifying these transients, so decaying lacquer from photometric surveys. So we wonder if it's feasible to do this using spectra, and it particularly relevant for upcoming large-scale spectroscopic time domain surveys. So the most important thing is the picture of this undergrad student, Alex Zander Dietman. So I promised him that I would highlight. So there we go. My job is done for today. I won't give you like a really detailed. So this is gonna be a broad brush thing. But you're welcome to look into the details if you're interested. So the idea is we know that there are supermassive black holes in galaxies. And we also know that sometimes, if you're really naughty, like for a star, like you can go close to it and then get disrupted, right? So there's a nice picture by folks simulated here. So what if you put these two cases together? So that's the question that we're wondering about. Okay, so this is the background slide. Nitrogen-rich quasars are a long-standing puzzle. They're a puzzle because their suggested metallicity is crazy. So it's anywhere between maybe 5 to 10 times solar. Okay, so I'm gonna let that sink in. For any of you who work on stellar evolution, you know that's a value that is difficult to explain in terms of the typical galaxy evolution path. But you may wonder, what about really close to the central region of the black hole? Perhaps a lot of enhancement is just happening really, really close to the center. Then, so solve this locally. Well, the problem is that it's really difficult to maintain this because these quasars, they're constantly accreting material, and so it's bottom line is really difficult to understand. The other sort of uncertainty here is, what if the observed nitrogen compared to other line ratio is just a main effect of the nitrogen abundance itself, right? What if the metallicity were just normal, but it's just something happened to the nitrogen? Well, the answer is that it's really difficult to produce just a nitrogen-rich material unless the absolute metallicity is really high. Okay, so it's a puzzle for us. And so I should explain the plot here. What you're seeing is the red curve is like a normal, for a normal Sloan quasar. So that's like a typical quasar I redshift 2 or 1. And is the composite of thousands of quasars. What you see is the usual like broad emission lines in the rest frame UV. So lemon and alpha, the strongest, but you also have carbon, like carbon 3, carbon 4, and other lines, and the of course the parallel continuum and the pseudo continuum from iron emission. So nitrogen-rich quasar really stands out, which is the black, shown in the black. This is just one of the strongest examples that we observe. So it's a huge ratio of nitrogen 3 over carbon 3. I'm going to be focusing on this line ratio in particular because the ionization potential of the two lines, nitrogen 3 and carbon 3, are very similar. So we're not subject to effects such as due to the shape of the ionizing continuum or the ionization parameter. They also have very similar critical density. Okay, so I think that's, yeah, and I should also say that they are a small fraction, so roughly less than 1% of all quasars. Okay. Okay, so this is the take-home slide. And, oh, sorry, I kind of gave away the punchline already. But, okay, so I was going to invite you to spot the difference. Okay, there we go. Of course, you now all made this discovery because I just point with the indicator there. So we were really surprised to see this. I should say that I didn't expect to see any like definitive example in this, just because the line itself is intrinsically so weak. So the best thing that I hoped for was some statistical evidence in general, which I will talk about at the later part of this presentation. Okay, so what's going on? So this is two spectra separated by about 2 years in the quasar rest frame, right? So we don't expect such rapid change. And if I can plot it, it's just in a different way so that will help us all better see the difference. So this is again the two spectra at the top and then the ratio spectrum directly at the bottom. So again, just to emphasize this, I can't do this enough, but it's really important to look at lines that are really sensitive to metallicity change, but not subject to other effects, which we also can calibrate. For example, we use like carbon 3 over carbon 4 ratio to see the effect, the change in the hardness of the ionizing spectrum. And the one line summary of this is that we observe about close to 90% decay in roughly 2 years. This is the most dramatic change observed in any nitrogen-rich quasar and in any quasar for that matters. And okay, so before I go and pretend I'm a theorist and then can actually explain this, but so let me just say that it's although it may seem like a small technicality, but I should emphasize that we need to look at the intensity ratio, not the equivalent width ratio. For galaxy people, but this probably doesn't matter because you have, your continuum doesn't really change, and you also have almost flat continuum. But for us, it really matters because if you just look at the equivalent width ratio, you might get puzzled. But we should really be looking at the intensity ratio that's being shown here. Okay, so what was going on in those 2 years? Was it just a statistical fluke? Well, maybe. So we went and looked at all the other spectra. So I should say the spectra were from the original Sloan and then the Boss survey. So definitely there could be systematic uncertainties associated with that. But we, after a list of different tests, we convince ourselves is unlikely to be explained by just a fluke. So we basically went and looked at, it's a big plate with a lot of spectra. We can look at other spectra on the same plate. We can look at individual exposures. So this is the co-add of individual 5 exposures. And we did a bunch of other tests. So the uncertainty that you saw there already included like systematic uncertainty due to, for example, changes in the continuum. So that we don't know where to put a continuum, right? Like how do you measure the emission, right? So bottom line is, like, it's really difficult to explain. In addition to that, we have statistical evidence. So the last 2 minutes, I will show you that not only in this single object, but we actually see evidence for this decay in the general nitrogen-rich quasar population, okay? So just going over through the possibilities. So metallicity change, highly unlikely considering the short time scale. What about ionization parameter, hardness of the ionizing spectrum? So again, really insensitive. So we're basically left out with this. And we are, for the record, we are not the first one to suggest this. So of course, we have theories, like many ideas. So this was speculated based on rest frame UV observations of known tidal disruption events in our local universe. So with the local TDEs, we're observing in the optical, but we know that TDE, they're the brightest in the rest frame UV, which is what we observe in these redshift 2 quasar. Okay. So I will refer you to the details on like a plausibility argument in which we estimated the detailed physics of this event, and it's consistent, but we unfortunately cannot provide a definitive proof because of the lack of a light curve that is long enough to allow us to trace both the peak and the decay of the event. We just caught it on the decay. Okay. So if I can have just 1 minute, this is the statistical evidence that put the single object discovery into context. I want to draw your eyes directly to the plot in the lower left corner. So this is the intensity change in the nitrogen 3 to carbon 3 ratio normalized by the uncertainty. Okay, so you're looking at, so for, and the difference between the color and the gray is that the gray is for really short time scale where you don't expect a lot of variability, whereas the color is the really long time scale, like longer than 1 to 2 years. Okay, and for the short time scale is consistent with just due to noise, both statistical and systematic. But the long term, the bottom line is like on long time scales, we do see a systematic statistical evidence for the decay in the overall nitrogen-rich population. Okay, so finally, I just want to emphasize the implication from this is that perhaps we're just seeing a really bright tidal disruption in these redshift 2 quasar, and is perhaps not crazy because if you think about for low redshift tidal disruption event, we're really seeing the religious tail of the SED, but for these high redshift quasars, we're close to the SED peak, which is why they're bright enough to be detected. Yeah, so I will just leave this here and then talk to me afterwards if you have questions.
Is there a simple argument that Quasar the supernova is so?
Yeah, so I don't think actually it will explain this just because of the spectral change in the. So we pretty much just have this evidence backed up by the the statistical sample. But I don't think that correct me if I were wrong here, but I don't think that supernova would give you such a large. Yeah, just this is I should say that this is really like empirical argument. It's not. You're right. Like perhaps it's also possible like to have a supernova like I guess really close to the center, and we're so lucky to catch it. But just from empirically, there are like UV spectral LTD just really resemble this. I guess that's the empirical argument, but that doesn't really say.
I've been working on respiratory UV spectroscopy of TVs, and from the few samples that we have, one thing that really struck me that's different from those is just like in the optical, we also see evidence for helium emission, and there just doesn't seem to be any in yours. Do you have any idea why that would be?
Yeah, so the helium line, as you can see in this particular example, is really weak. Although the black hole, so the width of the emission line is so broad, so it's really difficult to tell a helium-2. But that's definitely one of the puzzles that we are having problem with the GD hypotheses, because usually, well, so in the rest-frame UV, I should say, you also see nitrogen-4 line, right? But not always. So that could be just due to the sort of the duty cycle. But for helium-2, I think so. There are three local TDEs that have rest-frame UV spectra. So that's a small number, but still, like we see helium-2 in all of the three. So that's definitely one of the difficulties that we have. So although I should say there is a selection effect because we specifically looked at these nitrogen-3 and carbon-3 lines due to the reason that I told you about at the beginning. So it could be just a selection effect. So I definitely strongly recommend people to follow up other lines just in general. And there is also the possible effect due to ionization, because helium. So these two lines, they're like 30 also electron volts, so which is very different from helium-2. So I'm not sure how that will play into effect, but there are arguments, sort of hand-wavy, that can explain this. Does that answer your question? Oh, yeah, sure. Yeah, let's talk later.
Okay. Can you hear me? Yes. Okay, so my name is Federico Fraschetti. I'm a staff scientist at the University of Arizona. I'm visiting here CFA for a few months, many months in fact. So if you have questions about this talk or other things, please don't hesitate to come and visit me. Just a second, let me. Okay. So I'm not sure how much time I have here. I'll try to be as fast as possible. Yeah. Okay. Thanks. So okay, I'm going to talk about an attempt which we have done recently to combine the theoretical problem of modeling the particle acceleration and escape. In particular, the acceleration is already modeled, but the problem is to have a consistent picture of the escape at astrophysical shocks such as the supernova remnant shock, with the problem of having a unified picture of the broadband spectrum of the Crab Nebula, where by broadband I mean between the radio and the multi-TeV energy. So I let here my collaborators and others. So the outline, as I just said, is to find on one side a connection between the particles which we are quite strongly convinced are accelerated at the shocks, for example, supernova remnant shocks, with those particles which we actually see on Earth, which are called cosmic rays. So the connection is how do actually, theoretically, consistently, we describe the escape from the shock. The second point is to find a connection, so going from microscopic scales of the energetic electrons at the nebula out to the broadband spectrum baseline of the Crab Nebula. And I apologize, I'm not talking about here the flares, even if there was just an observation last week. So we're working on this. Cosmic rays were discovered about 100 years ago, a little bit more than that, by Victor S. We know now that they are distributed over a huge range of energies. They are produced by different sources with different mechanisms, with different time scales. But basically they are seen everywhere in space where the density is low enough to allow for their existence, which means you need charged particles interacting in a collisionless way with magnetic field turbulence. There is quite a well-established model which is called diffusive shock acceleration. Many of you are probably familiar, which was discovered surprisingly by several people in just a short interval of time. The list is up there. Is that, I saw a pointer before, but it's no. Thanks. Okay. How did you just do so? Oh, this one. Okay, so this list here. You can derive with two different ways the main prediction of the diffusion shock acceleration theory. One is a probabilistic individual particle approach, which is basically based on asking the question, what is the probability that the individual particle remains nearby the shock in the acceleration region and can continuously cross it and being thereby accelerated instead of being, for example, vectored downstream. And you can calculate this probability for accelerated particles still being accelerated, but already at energies a little bit higher than the thermal energy, is constant in the particle energy. Second important ingredient is that these particles must have a speed higher enough as compared with the shock speed in upstream frame, that they have time to do many scatterings in the local plasma frame, and so to be isotropized. So isotropized, when I say isotropy, I mean isotropy with respect to the pitch angle, which is the angle between, as you know, the velocity vector and the uniform magnetic field. So with this approach, you can derive a momentum distribution unidimensional, which is a power law, as most of you, I think, know. But there is a second way, which is solving directly the transport equation for a shock which is infinitely planar and in steady state. This method also provides a power law, which depends only on the shock compression, in the case that the cosmic rays do not have a feedback on the structure of the shock. If the pressure of cosmic rays, for example, is comparable with the RAM pressure or with the thermal pressure, this condition is not satisfied, this result is not fine, and you find typically a curve, a spectrum which is a little bit concave. So this is an example of deviation from power law. The problem arises when you want to connect accelerated particles with cosmic rays, so particles which escape. So how to describe escape from the shock? One way is reiterating the probabilistic approach, asking what is the probability that the particle has energy high enough to escape from the system. Visually, you can see this if you compare the mean free path of those particles upstream of the shock. This is the upstream and this is downstream, if you compare the mean free path absolute shock with the diffusion length, which is approximately kappa, so the spatial diffusion coefficient in the direction of shock motion divided by the particle speed. So this is the distance at which more or less particles can be kept close to the shock because of scattering. If the mean free path becomes comparable, even larger than that, of course you cannot contain particles anymore there and they just escape. A way to describe this probabilistically is to define this probability of remaining in the acceleration region as a quantity which decreases with the particle energy. For example, this way. So the most energetic particles just have to leak out. And from this assumption, you can derive this energy spectrum for the particles, which is a so-called log parabola. Here is a illustrative picture. So it's just a parabola in the log-log scale. You can see that if beta is equal to 0, you collapse back to the ordinary parabola. So, the ordinary power law. So what is the likelihood to see log parabolas in space? In fact, it's quite large, and there are many different examples. The first time it was derived and applied is the modeling of the steady-state spectra, X-ray spectra of the blazars. But there is also a case where it was applied to the shock of supernova remnant, for example, SNSO6. So here we are in the regime of non-relativistic shocks. There is also a significant fraction of photon spectra in the third galactic Fermi-Lat catalog, as you can see here, which are fit with log parabola instead of power. These are, of course, photon spectra. But if you go back to the observation of interplanetary shocks, so those which travels between the Sun and Earth, there you have spacecraft which can really measure in situ the distribution of energetic particles. So you're not only probing the emission, you are really measuring the intensity of particles and testing the diffusion shock acceleration model. Here I took an example of shock from this spacecraft data and fit with the band model, which was familiar with GRBs know, who's not, I can explain more later. And this turquoise is the fit with the log parabola. So there are many different cases in many different regimes where, in fact, the log parabola seems to be observed. Second part is to connect all this with the pulsar wind nebula, in particular the crab. So this is the very schematic picture of the nebula end termination shock, which is given basically by the equilibrium between the wind run pressure which pushes outward and the containing nebular pressure which pushes inward. And this is basically a quasi-perpendicular shock because the magnetic field is just carried with the fluid against the shock surface here. So the magnetic field stays more or less on the surface of the shock. And it's quite well known, it's been quite well known for a long time that these shocks can accelerate particles very efficiently and very fast. This is an example of broadband fitting of the Crab nebula. So there is now the Crab nebula spectrum. And you see it's quite complicated, and it's even more complicated, the microscopic modeling. So this is one of the different populations which for this model are used to feed the data. So this is a combination of a power law, which is what you normally expect for shocks, but is with an exponential cutoff. So that's the typical way that the escape is described with a sort of empirical approach. And this is done all with a magnetic field which is uniform throughout the nebula. So, one to last slide. This is what we have done here. So, we have taken a log parabola distribution of electrons, assuming they are accelerated all at the termination shock of the nebula, and then we solved the transport equation for those particles, taking into account the losses over the lifetime of the nebula, which is about 1,000 years old. So, this gives you a consistent picture of the combined synchrotron and the very energy part, which is the synchrotron self-compton. So the photons which are emitted by synchrotron are then upscattered by the same electrons to higher energies. I'm done. There is just one caveat that there is the global spectrum, but of course detailed studies with higher spatial resolution find different things in different regions of the nebula. So we are not overlooking the fact that you can have a spatial dependence on the spectrum. We are still working on this. And another important point is that it is analytical, so you don't need computers to do this. Final point, the Crab Nebula are confirmed, if all this is verified also for other sources, are confirmed to be an important astrophysical laboratory. I want to point out that we derive this with a microscopical approach. So I repeat, we use just a probabilistic approach, which is the twin of the probabilistic approach usually that usually supports the diffusive shock acceleration. Of course, you need to do this also solving transport equation, and this is underway now. This means, if all this true, means that the models of acceleration supernova Riemann shocks need quite a substantial revision. Means that when you look at power law, you are already looking at quite narrow energy interval. But if you combine different spacecraft in broader energy band, you might see something different, which is not necessarily power law plus exponential cutoff, but something else. And finally, this is certainly applicable to many other sources, pulsar with nebula, supernova remnants, and we are working with different people using different facilities to test this. Thank you. Well, everybody's tired. Sorry? Everyone agrees? Yeah. Everybody. Okay. Thank you. Thanks. But this is yours. Okay. It's a good one, shot. But the shot is maybe narrow, but the red is much better than the green. Sometimes when you have the green, it's just hard to see. Oh, yeah, you're right. We're still recording. Oh, shot it is.
Okay, bye.